Alright, so in this video I'm gonna be explaining this article towards unified and effective domain generalization. So when we say domain generalization, it means that we are dealing with unseen domain. We want to see what happens when we have unseen domains. So this paper in 2023. And the rest of the articles here are very related to this idea. We propose UniDG, a novel and unified framework for domain generalization that is capable of significantly enhancing out-of-distribution generalization performance of foundation models regardless of their architectures. The core idea of UniDG is to fine-tune models during the inference stage, which save the cost of iterative training. Specifically, we encourage models to learn the distribution of test data in an unsupervised manner and impose a penalty regarding the updating step of model parameters. The penalty term can effectively reduce the catastrophic forgetting issue, as we would like to maximally preserve the valuable knowledge in the original model. So this is a large-scale pre-trained foundation models are still suffering from domain shifts. When we go to these sketches, then only 10% accuracy, and it's too low. But you may be proud of your large-scale pre-trained, but the reality is that only 10% works in another domain. When we want to transfer it to a different domain, such as sketches of this type, and we first reduce the formulation of domain generalization and test time adaptation. We first introduce it. The framework comprises of two components. We employ marginal generalization to adapt the encoder. We utilize prototypes with differential memory bank for learning a discriminative classifier on the target domain. So you see the whole framework here. We have pre-training stage that we have this data from number of S domains. We give it to the source encoder and then we classify it because we have the label for that. But then we have a marginal representation generalization that we have adapted encoder and differential memory bank, and we are doing this marginal generalization. And we use this differentiable memory bank that we will explain. So given a set of domains, source domains, each domain containing its image and label. And then we denote the mapping function of a model from X to P. P is a prediction. C is the number of categories. Here, number of categories. So we have two steps. The feature extraction, as I said, with encoder F, and the prediction end with the classifier. First, we train on source domains. We always use cross entropy. It's a simple classification. And then at the test time, with theta star that we have obtained here, test time adaptation is self-supervised learning. And the encoded parameters during test time can be optimized as the following. So this L is again a softmax entropy. So marginal generalization aims to constrain the discrepancy between features extracted by the source encoder and the adapted encoder. So both F and F prime are source, and so F is source encoder, F prime is the adapted encoder, And the adapted model will be able to maintain general representation bias and relieve this term. Catastrophic forgetting comes from continual learning. I have a playlist for continual learning. What was one of them was this idea of Fisher information matrix times when we want to fix the when we don't want to change the weights, we want to force or encourage the parameters of the second task to be very similar to the first task, or the second stage very similar to the first stage. And when F is this Fisher information matrix is constant, it becomes just a starting point regularizer. The same idea, they're using it here. They have adapted encoder and the source encoder. They want to make sure that the difference between them, in terms of Frobenius distance, Frobenius norm between these two, is less than we solve this optimization such that this distance is less than a threshold. We call it distance threshold. So you see the connection between that idea in continual learning. It is still the same task. It's not like continual, but we draw inspiration from this idea that we don't want to catastrophically forget that. So the motivation is that we desire to gradually update the parameters of the adapted encoder under the condition that the representation bias will not get sharply adapted. For the source feature extractor, we freeze it and still use it to extract the representation from target domains as pre-trained knowledge. For the adapted encoder, we initialize it with the source pre-trained parameters. Therefore, the discrepancy between original and the adapted can be formulated as this distance. And then to approximate such a hard constraint with backpropagation, because how do you want to implement this with a neural network? You need to do this trick. We call it marginal loss. If the distance between, so this one comes here, minus sigma is less than 0, so that's why this 0 comes. So it becomes like a marginal adaptation loss. So with this trick, we can solve now this optimization problem. And so the update of the parameters of classifier and encoder is guided by the entropy on the target. So with marginal generalization, we are able to learn a well-adapted encoder that can extract discriminative features in the target domain. However, since there is no labeled data in the target domain, only training with the unsupervised losses, it's hard to get a classifier with high performance on the target. To mitigate this issue, we propose to update the classifier with a differentiable memory bank. We utilize memory bank to select prototypes suitable for the new domain. Develop classifiers prototypes directly differentiable with loss function. So classifiers prototypes are stored in the memory bank in order to enhance the classifier. Specifically, for each class J, the prototype V sub J is initiated with the corresponding weights of the source classifier layer. In the self-supervised adaptation process, for each target sample X, We extract a representation f prime and obtain the output of classifier q prime. Then we predict pseudo-labels and utilize the entropy between the representations and pseudo-labels as the criterion to select the top k instances of each class with highest classification confidence, where k is just a hyperparameter. So we utilize the representation of top k samples to produce this class-wise prototype. And memory bank is set to store the prototypes of each class. For a given sample x, we have this feature z. So z comes here because we have a feature representation of that and the classification probability of class J, because remember this is the prototype for class J, can be computed like this. So omega sub j is just the jth element of the weight matrix. So we are learning it. And here the marginal generalization is proposed to learn a well-adapted feature encoder without catastrophic forgetting. And a differential memory bank is proposed to learn a discriminative classifier. So two different losses. While updating omega with target prototypes, the overall learning objective is this. And so this is the algorithm. We copy a new model with the source one and freeze f and q. So we freeze the feature extractor and the q, which is pre-trained from the source model. Then we go through this loop. We arrive target data, we update the prototypes, we calculate, we have two losses here, LM, and for individual. And so these are the experiments VLCS, 5 classes from photographic data sets, and the standard errors of classification accuracy is used for evaluation metric. So you see that in domain generalization, we don't go from one source to the target. We don't do this because it's a generalization we should do for individual domains. For example, for these domains, different algorithm. For example, the paper says this is their performance. And they also reported their accuracy. They use ResNet 1850 for backbones. And you see different backbones, backbone network. For example, instead of ResNet, sometimes they call it MobileNet. They use different backbones, such as even EfficientNet. And there are different types. For example, a transformer can have different backbones. A multi-layer perceptron can have different backbones.